In this video, we're going to continue our discussion on integration by talking about improper integrals. Now, improper integrals are going to look kind of like our definite integrals, integral from a to b of f of x dx, except instead of just considering continuous functions on finite intervals a to b, one of these values, a or b, or both, could be infinite. And we could also have a case where maybe the function has an infinite discontinuity in the interval a to b. So we have to deal with different types of infinity while doing a definite integral. So let's just start right away with an example so we see what's going on here. So let's just consider the region S that lies under y equals 1 over x squared above the x-axis and to the right of x equals 1. So what this looks like, here's 1. We're talking about this region here, and it's going on forever. And we want to talk about what the area of that region is. So this region here, it goes on forever to the right, but it gets really, really skinny. And your first instinct might be that that area should be infinite because it goes on forever. And that's not always true. To figure out what this area is, we're going to start by just chopping it off at one particular place, t, and we'll find the area between 1 and t first, and then take a limit as t goes to infinity. So the area between 1 and t is given by the definite integral from 1 to t of my function dx. And I can calculate this by rewriting it with a negative exponent and then doing my antiderivative. So my antiderivative ends up being a negative x to the negative 1. We'll plug in the t and plug in the 1. And that, of course, is the same thing as negative 1 over x from t to 1. So I get a negative 1 over t minus a negative 1 over 1. So I get negative 1 over t plus 1. And now if I just imagine taking my t bigger and bigger, what happens to this area? As t goes to infinity, what happens to the area? Well, we would have that the area is the limit as t approaches infinity of this answer that we had, negative 1 over t plus 1. But now if I imagine t getting bigger and bigger, that makes that negative 1 over t smaller and smaller and smaller. It goes to 0. So this limit is equal to 1. This means the area of S is 1. And we write that the integral from 1 to infinity of 1 over x squared dx is equal to the limit as t approaches infinity of the integral from 1 to t of 1 over x squared dx. And we found that that was equal to 1. And what we did here is actually an improper integral. We had an integral that had an infinity for one of the bounds, and we redid it using a limit and found out we had a finite answer. So now let me give you the exact, more formal definition of our improper integrals, and we'll do some more examples. So here's our definition. if the integral from a to t of f of x dx exists for every t bigger than or equal to a, then we have that the integral from a to infinity is equal to the limit as t approaches infinity of the integral from a to t. Provided that this limit exists as a finite number. So to calculate one of these integrals where you have a number to infinity as your bounds, you rewrite it as a limit, do that integral, take the limit, and find out if you have a finite answer or not. That's one version of our improper integrals. Another version is very, very similar. So I'm just going to keep most of this up here and just rewrite it. So the second part says, if the integral from t to b of f of x dx exists for every t which is less than or equal to b, then the integral from negative infinity to b is equal to the limit as t approaches negative infinity of the integral from t to b, provided this limit exists as a finite number. So regardless of whether you have an infinite bound for the upper bound or the lower bound, you rewrite it using a limit, calculate it that way, and if you get a finite result, then that integral with the infinite bound is equal to that result. Now, we say that both of these types of integrals here are convergent if that limit exists as a finite number, and otherwise we say it's divergent. So if the limits in A and B exist as finite numbers, we say the integrals are convergent. Sometimes we also say the integral converges. And otherwise, the integrals are divergent. So if you calculate the integral using a limit and you get a finite number, then your integral converges. If you get an infinite number, your integral diverges. And now I needed that for part C of our definition. If the integral from a to infinity and the integral from negative infinity to a are both convergent, then the integral from negative infinity to positive infinity of our function is defined to be the sum of these two integrals. So what this is saying is if you have an integral from negative infinity to positive infinity, split it into two, dividing it at some number. You can pick the number. Usually we pick 0, but you can pick whatever number you want. And then you have two integrals to calculate. If they both converge, then you can define the original integral as the sum of those two results. Let's do another example. Is the integral from 1 to infinity of 1 over x dx convergent or divergent? Well, to figure out if it's convergent or divergent, you should just try to calculate the integral. If you get a finite number, you know it's convergent. If you get something infinite, you know it's divergent. So I'm going to rewrite my integral using a limit. I'm going to have the limit as t approaches infinity of the integral from 1 to t of 1 over x dx. And now let's just do the integral and calculate the limit. So I'm going to have a limit as t goes to infinity of antiderivative of 1 over x is natural log absolute value of x. Plug in the t and plug in the 1. So when I plug in the t, I get the natural log of absolute value of t. And when I plug in the 1, I get a natural log of absolute value of 1. But we know the natural log of 1 is 0. So this is just the limit as t goes to infinity of natural log of t. So as t gets bigger and bigger, my natural log also gets bigger and bigger, and this limit is infinite. And that means that my integral is divergent. And that's all there is to it. Sometimes you're going to get a finite number, other times you're going to get something infinite. If it's infinite, it diverges. If it's finite, it converges. Let's do another example. Let's evaluate the integral from negative infinity to 0 of x times e to the x dx. And the first thing I would do is rewrite this right away with a limit. So I have a limit as t goes to negative infinity, integral from t to 0 of x e to the x dx. Now how do we do this integral? Integration by parts. So yes, even when doing improper integrals, you might have to use integration by parts, trig identities, trig substitution, regular substitution, even our partial fractions. All of that is completely doable using improper integrals. But this one is integration by parts. So I need a u and a dv. I would pick u equals x and dv equals e to the x dx. I chose it that way because if I chose u equals x, well then my du becomes simpler. It's just dx. I got my exponent to get smaller. And if dv is e to the x, then v is also e to the x. So calculating our integral, I have a limit as t goes to negative infinity of u times v, so x e to the x, evaluated at 0 and t, minus the integral from t to 0 of v du, e to the x dx. And let's go ahead and just calculate that integration all the way through. So I'm going to have a limit as t goes to negative infinity of x e to the x minus e to the x evaluated at 0 and at t. Now, when I plug in the 0, I'm going to get, well, we get 0 for the first term, and I would get negative 1, because e to the 0 is 1. And now I need to subtract what I get when I plug in t. So I get t e to the t, and minus the negative, so plus e to the t. And we just need to calculate this limit. And let's take a look at this piece by piece. So I know that this negative 1 is going to stay as negative 1. This guy in the middle is a little complicated because I'm having an infinity times an e to a negative infinity that would go to a 0. I don't really know what that is. We'll have to deal with that separately. But I do know that this e to the t, as t goes to negative infinity, this gets smaller and smaller. That guy goes to 0 because the fact that my exponent is negative. So I have a 1 over e to a large power. That guy goes to 0. So far I know I'm going to have my minus 1, and I just have to figure out the limit as t goes to negative infinity of this middle guy here. I'm going to rewrite it as minus and just have the limit of t e to the t. So again, this is of the form negative infinity times 0. We don't know what that is, but I can rewrite it and evaluate it differently. I can rewrite this as a t over e to the negative t. And now my numerator goes to negative infinity and my denominator goes to positive infinity. So I'm in a proper form to be able to use L'Hopital's rule. So doing L'Hopital's rule, I still have my negative 1 in the front. I have my minus limit as t goes to negative infinity. On the top, I get 1, and on the bottom, I get negative e to the negative t. And now let's rewrite that again. Rewriting so I don't have a negative exponent. I'm going to have negative 1, pull this negative in front of the limit, so I get plus a limit as t goes to negative infinity of e to the t. And now this limit here, e to the negative infinity, well, we're getting closer and closer to 0. So I have a negative 1, this guy goes to 0. My final answer is just negative 1. So if I asked, does that integral converge or diverge, your answer would be the integral converges to negative 1. Okay, let's do one more example of this type of improper integral, and then we'll learn about the other type. Let's do an integral from negative infinity to positive infinity of 1 over 1 plus x squared dx. Well, I have two infinite bounds of integration, so I'm going to split it in the middle. This is equal to an integral from negative infinity to 0 of my function, plus an integral from 0 to infinity of my function. And we know from our definition that provided that both of these integrals exist and are convergent, so the limit ends up being a finite number, then I can just add the results to get the answer to the original integral. So let me just do the first part here. So the integral from negative infinity to 0 of 1 over 1 plus x squared, I would rewrite as a limit as t goes to negative infinity, integral from t to 0 of 1 over 1 plus x squared dx. And the antiderivative of this 1 over 1 plus x squared is an inverse tangent. So for this first improper integral, I get the limit as t goes to negative infinity of the inverse tangent of x evaluated at 0 and at t. Now, when I plug in inverse tangent of 0, I'm going to get 0. So I just have a limit as t goes to negative infinity of the inverse tangent of t. And that happens to be equal to I forgot my minus sign, so I was subtracting that lower bound. So this is equal to the limit as t goes to negative infinity of negative tangent inverse of t. That's negative pi over 2, and that's just pi over 2. Now, if you did not know what this limit is of your inverse tangent, you might want to remember what the graph of the inverse tangent function looks like. And you would find that you have a horizontal asymptote on the left side of negative pi over 2. That graph of inverse tangent, just a really rough graph, looks something like this, where I have horizontal asymptotes at pi over 2 and negative pi over 2. So we were talking about the limit to negative infinity. That would be that negative pi over 2, but I had a negative in front of it, so I got pi over 2 for that improper integral. So I got the first improper integral converged, and it converged to pi over 2. Now let's look at the other one, the integral from 0 to infinity of my same function. Well, that's a limit as t goes to positive infinity, integral from 0 to t of my function. That's limit as t goes to infinity of my inverse tangent of x, evaluated at t and at 0. So I get my inverse tangent of t, and then minus inverse tangent of 0, which is 0. This limit gets me pi over 2. That's my other horizontal asymptote. So both of my improper integrals equal pi over 2, and they're convergent. And so this tells me that the original problem the integral from negative infinity to positive infinity of 1 over 1 plus x squared, this is equal to the sum of the two improper integrals that we already calculated. So this is pi over 2 plus pi over 2, which is pi. And so this integral here, negative infinity to positive infinity of 1 over 1 plus x squared, gives me pi. All right, so that was a whole lot of examples where we have one bound that's infinite or both. And now we need to talk about the other type of improper integral. And that's where if we have some form of a vertical asymptote. So first, if our function f is continuous on a to b, but discontinuous at b, then the integral from a to b of our function is equal to the limit as t approaches b from the left side of the integral from a to t of our function. If the limit exists as a finite number. So for this first definition, notice that it's very similar to what we did with the infinite bounds of integration, except instead of having an infinite bound of integration, my function is undefined at one of my bounds. I had my function with discontinuous at that b, so maybe we're dividing by 0 there. And so we rewrite as a limit to take care of the problem. If that limit exists and it's finite, then we have a convergent integral. For part B, if your function is continuous on the interval a to b, this time not including a, so we're discontinuous at a, then the integral from a to b of our function is equal to the limit as t approaches a from the right side of the integral from t to b. provided the limit exists as a finite number. So again, all this is saying is wherever you have a problem, whether it's an infinite bound of integration or your function's discontinuous there, you rewrite it as a limit to hide the problem. Then if the limit exists as a finite number, you have a convergent integral. Otherwise, it's divergent. Now, both A and B for this definition involve the function having issues at one of the endpoints of our interval. But it's also possible that your function could have an issue somewhere in the middle of the interval. So if your function has a discontinuity at C, where C is some number in between A and B, and both the integral from A to C and the integral from C to B of our function are convergent, then we define the integral from A to B of our function as the sum of those two integrals. So what this is saying is if you have an issue somewhere in your interval, so you have a vertical asymptote in the middle of the interval that you want to integrate, well, then you should split it up into two improper integrals at the point that's causing problems. Calculate each of these using the definitions we showed in A and B, and if they both exist as a finite number, then you can add the results to get the original answer. So I have a couple examples of this. Let's find the integral from 2 to 5 of 1 over the square root of x minus 2. Now, prior to this video, you would look at a problem like this and just assume everything's all good. But we have an issue here. My function has a discontinuity at one of the bounds of integration. If I plug in x equals 2, I'm dividing by 0. So we can no longer assume that anything that looks like a definite integral is just a definite integral. We might have an improper integral. You always need to check if your function is continuous everywhere between the bounds of integration. So I have a vertical asymptote at x equals 2, one of my bounds of integration. So I can rewrite my integral using a limit to take care of the problem. So I'm going to have a limit as t approaches 2 from the right side of the integral from t to 5 of 1 over the square root of x minus 2. Now, how do I actually calculate that? Well, we're going to have to do a little mini u substitution. If I let u equal x minus 2, well then du will be dx. Changing my bounds of integration, when x is t, well, that means that u is going to be t minus 2. And when x is 5, then my u is going to be 5 minus 2, which is 3. So rewriting my integral using my u substitution, I have a limit as t approaches 2 from the right side of the integral from t minus 2 to 3 of a 1 over square root of u du. Now, 1 over square root of u, I can rewrite that as a u to the negative 1/2 power. So let me just rewrite my entire integral I have a u to the negative 1/2 power. And now I can do the antiderivative. I have my limit as t approaches 2 from the right of the antiderivative of u to the negative 1/2. So I'm going to add 1 to the power, u to the 1/2, and then divide by my new power. So I get a 2. Then I'm going to plug in the 3 and plug in the t minus 2 and see what happens when I take my limit. So remember that u to the 1/2 is the square root. So I'm going to rewrite it as a square root when I finish this up. The limit as t approaches 2 from the right of 2 times the square root of 3 minus 2 times the square root of t minus 2. And now what happens when I plug in values for t that get really, really close to 2 from the right side? Well, this guy's going to get really, really close to a square root of 0, which is 0. But notice that it's completely well defined because I'm plugging in numbers that are larger than 2, so I don't ever take a square root of a negative. So this guy here goes to 0 when I take the limit, and that means the answer to the entire problem is just this 2 times the square root of 3. And that's the answer to the original integral. So yes, sometimes you have to do substitution on these problems too, and you always need to check, is my function continuous everywhere between my bounds of integration and at my bounds of integration? If it's not, you need to rewrite it using a limit and calculate it that way. Let's do one more like this. Does the integral from 0 to pi over 2 of secant x dx converge or diverge? So at first glance, this looks like it's just a definite integral. I don't have any infinite bounds of integration. But remember, secant is 1 over cosine. And cosine at pi over 2 is equal to 0. So we have a vertical asymptote at pi over 2 where we're dividing by 0. So we have a vertical asymptote at x equals pi over 2. That means I need to rewrite my integral using a limit. So I'm going to have a limit as t approaches pi over 2 from the left side of the integral from 0 to t of secant x dx. Now, the antiderivative of secant, I gave you that formula in one of our more recent videos. The integral of secant is natural log of absolute value of secant plus tangent. So I have a limit as t approaches pi over 2 from the left side of the natural log absolute value of secant x plus tangent x evaluated at t and at 0. So when I plug in the t and plug in the 0, what do we get? Well, when I plug in the t, I'm going to have a natural log absolute value of secant t plus tangent t. What happens when we plug in the 0? Well, secant of 0 would be 1, and tangent of 0 is 0. So I'd have a natural log of 1, which is 0. So I don't need to write that down. All I have left to calculate is this limit here. And as we approach pi over 2 from the left side, well, my tangent of pi over 2 ends up being a 1, but secant of pi over 2 goes to infinity. So I get infinity, and my integral diverges. All right. So that's about it for this section here. When you're doing improper integrals, you just have to make sure that you check to make sure your function is defined everywhere in the interval. If it doesn't have infinite bounds already, rewrite as a limit for whatever the problem is. If you have infinite bounds of integration, use a limit to hide the infinite bounds. If your function's discontinuous somewhere, use a limit to hide the problem. Regardless, you end up doing an integral, taking a limit, and if you get a finite result, the integral converges. If you get an infinite result, the integral diverges. If you have any questions, feel free to drop them below. If you're a current student, you can also ask in office hours, in email, or in person, and I'll see you guys next time.